With these two equations in hand, let's just substitute in this more detailed expression for the partial molar free energy in solution in the top equation on the right-hand side into the left-hand side of the bottom equation. So it's still a sum over all substances involved in the reaction, but now instead of the partial molar free energy of solution, we have this more explicit expression, the standard molar free energy of the pure substance plus RT natural log of the mole fraction of that substance in the reaction mixture. Now, in this case, we're looking at a very specific type of ideal solution, a chemical reaction, times the stoichiometric number, and that must be equal to 0. Let's now multiply through by nu I and separate the terms. So we have a sum over all the reactants and products indexed by I, nu I times the free energy of the pure substance, the molar free energy of the pure substance. And now I'm going to multiply through by nu sub I and then move the second term over to the right-hand side so that it becomes negative. Negative sum now over all the reactants and products, nu I RT natural log of the mole fraction of the ith component in the reaction mixture. Let's go back now to our example of ethine reacting with HCl. Using the convention of stoichiometric numbers, we can write that reaction almost as a mathematical equation. Negative C2H2 minus 2HCl plus 1 C2H4Cl2. So what does that make the left-hand side of this bottom equation here? Let's do the sum specifically for this reaction. We have the molar free energy of pure product, C2H4Cl2. I'm going to start with the products, times positive 1, since its stoichiometric number is 1, minus, since the stoichiometric number of C2H2 is negative 1, the molar free energy of C2H2, minus 2 times the molar free energy of HCl. What is this sum, really? We're taking the standard free energies of the products and subtracting the standard free energies of the reactants. Well, this is just delta G of the reaction. This is just the standard molar free energy change for the reaction itself, something we could calculate using, for example, free energies of formation or enthalpies of formation and entropies, right? Out pops delta G of reaction. So now you can see we're getting very close to the finish. We're halfway there. All that's left really is to elucidate this products over reactants portion, since RT is there, delta G is there, and it's clear where the exponential is going to come from since we have a natural log floating around in the equation. So the left-hand side is just equal to delta G of reaction, the standard molar free energy change of reaction. What about the right-hand side? Well, RT is a constant, so let's kick it out front with the negative sign. And inside the sum, let's recognize that nu I times the natural log of xi is equal to the natural log of xi raised to the power of nu I. We've seen this before. This is just kicking a factor multiplying a logarithm inside the logarithm, which raises the argument to that power. Moving this expression kind of up and to the right, we can now just divide through by negative RT, and so that the left-hand side is negative delta G of reaction divided by RT, and the right-hand side simply becomes a sum over the reactants and products of the natural log of the mole fraction raised to the stoichiometric number. We are very nearly home free. This is a sum over logarithms. That is the same as the natural logarithm of a product. And so I'm going to replace the sum with a product and move it inside the logarithm, x sub I, nu sub I. And now hopefully you're seeing where the products over reactants idea comes from. For the products, nu sub I is positive, leaving this in the numerator of this product. For the reactants, nu sub I is negative. That puts x sub I to the nu sub I in the denominator of the resulting expression, right? So another way to write this is, for example, for our specific case, in fact, of C2H2 reacting with HCl, we could write this as the mole fraction of C2H4Cl2, the product, raised to the positive 1 power. So we often don't include that, but I'll include it here just for clarity. Divided by now, since these stoichiometric numbers for the reactants are negative, x for C2H2, x for HCl, squared. It uses mole fractions instead of molarity or pressures, but I hope you can see that this is just the equilibrium expression. It's popped out. It's the argument of this logarithm. And finally, when it's all said and done, and we take the exponential of both sides, we raise e to the power of both sides of this equation, we get the magical result. E to the negative delta g over RT is equal to the mole fraction of all the products raised to their corresponding powers, divided by the mole fractions of all reactants raised to their corresponding powers. Both of these are collectively equal to the equilibrium constant K. Just in the interest of time, I won't go into why these are mole fractions instead of molarities and how we can convert from mole fractions to molarities, but it'll suffice to say that as long as we agree on the standard free energies of the pure substances, we can use either mole fractions or molarities. So this was a very long derivation, and I congratulate you if you got to the end of the video, but it does illustrate a couple of things. First of all, it illustrates the nature of the delta G that goes in this expression, which is a common point of confusion, actually. It's the standard molar free energy change of reaction that goes in the argument of this exponential. This delta G does not depend on reaction conditions, right? Since the little circle tells us what the reaction conditions are, essentially. That should make sense because the equilibrium constant is not dependent on conditions. Its value is what it is regardless of the concentrations of reactants and products. In a sense, the value of K is innate to this reaction carried out at a particular temperature and pressure, but it has nothing to do with the mole fractions or the concentrations of reactants and products. K is what it is with respect to concentration.